So Taylor series. So Taylor series is actually a wonderful way of relating the derivative of the function. Actually, a lot of orders, any derivative to the function, any higher order derivative to the function, related to the values of the function at different points. So for example, the simplest approximation to Taylor series analysis The simplest application to Taylor series analysis is involved in the first order derivative, actually. So let's say I have a function w as a function of x, and I have 2 points, x0 and x1. I know the value of the function at x0 being w0. I know the value at x1 being w1. An intuitive way to compute the first order derivative of the function near these 2 points, I mean, imagine these 2 points are very close, is actually, a lot of you said, the slope, right? Which means the derivative of the function dw dx can be approximated as w1 minus w0 divided by delta x. So this is actually an application of the Taylor series analysis. Why is that? That's because w1 being w at x1, well, by the way, delta x is x1 minus x, I mean, it's actually defined as x1 minus x0. So wx1 is actually can be expanded into this so-called Taylor series analysis. So first of all, the first term of the Taylor series is w at x0. So which means if I only keep the first term, it's a very gross approximation of the value at x1. It's an approximation by a constant. Okay, so it's approximation by this constant value, which means I'm approximating the value at x1 as the same as the value at x0. This approximation actually works not too bad if x1 is extremely close to x0, right? So this is called a 0th order approximation. Very crude approximation, works only very well when the 2 points are very close. Now, how do I improve on that? The way to improve on that is to use this intuition, right? If I know the first order derivative of w at x0, I can actually approximate the value at w1 to be here. So if I know the first order derivative of the function over here, I can basically linearly extrapolate. And the value w1 can be approximated by this term plus a blue term. That is the derivative of w at x0 times x1 minus x0, right? So this is basically the slope times the distance. And the second term is this. This is dw dx times x1 minus x0. So basically, I added a term on top of the zeroth order approximation to get my first order approximation. So this first order approximation works better when when x1 minus x0 is not that tiny, right? But like when the distance between them is larger, this again is going to fail. And then I can add more and more terms onto this. The next term is actually accounting for if that function is a smile or a frown, right? So if the second order derivative is positive, I should add another term onto it. If it's negative, I should subtract a term on it. And the second order derivative term is the second term in the Taylor series analysis. It's a half of the second derivative of w, again at x0 times x1 minus x0 squared. And this approximation actually can go on and on and on. And mathematically, you can prove that if I add more and more terms onto it, let's use black to represent the more general term, plus 1 over, let's see, what symbol should I use? Let's use K. I didn't use K before, right? Well, this is kappa. Let's use M. M factorial. The mth derivative of w to x. Oh, well, let's use d. I only have a function of one variable at x0 times x1 minus x0 to the mth power. And keep going. So if I add infinitely many terms onto it, it's going to be exactly going to be equal to w1 for all analytic functions, which encompasses a lot of, it's basically most of the functions you can write out are analytical functions, right? You can construct a lot of pathological cases that for this doesn't converge, but almost any functions you write out are analytical functions. So Taylor series analysis is a very, very powerful way to approximate smooth functions, right? So for functions which this doesn't work, are obviously functions that are not continuous. If you have a discrete jump, well, Taylor series of course doesn't work. But for all smooth functions, one-piece functions you can write out analytically, Taylor series is going to converge exactly. And what does it mean by converges? I mean, what does it mean by the infinite series converge? Right. So series conversion means no matter how accurate you want it, you can always have a finite term, right? Finite. You can always have. You always know that for large enough number of terms, you are going to be close enough to whatever criterion you impose. Right? Mathematically, for any epsilon, you can have a large enough n, so that if you have more than that many terms, your accuracy is better than epsilon. Okay, so this is this means you can always have a sufficient number of terms that if you truncate the Taylor series, you are very accurate. Another thing you can observe is that, which is particularly true if x1 minus x0 is small, is that the high order terms, they actually decay very fast. Right? So for example, assuming the same function, right? Assuming the same function, which means that the derivatives are the same. If x1 minus x0 is shrinked by a factor of 10, the 0th order term, wx0, doesn't change. While the first order term is shrinked by a factor of 10. The second order term shrinks by a factor of 100. The third order term shrinks by a factor of 1,000. And the 100th term shrinks by a factor of, oh, actually I don't know what it is, but like 10 to the minus 100. So basically, as you shrink the distance between x0 and x1, my high order terms becomes negligible very fast. Okay, so that again brings out the concept of high order schemes. So the order of a scheme for approximating differential equations relates to when I shrink my distance between adjacent grid points, how fast does my scheme get more accurate? Right, so a first order scheme means if you shrink my delta x by a factor of 10, the accuracy of the solution also gets better by a factor of 10. Right? A second order scheme means if I shrink my delta x by a factor of 10, my solution gets better by a factor of 100. Right? So I mean, they seems to be very good until you consider that I have delta x and delta y and delta z and delta t. And if I shrink all of these directions by a factor of 10, my computation cost actually goes up by a factor of 1,000. Anyway, we can discuss this later, but like this is Taylor series analysis. And Taylor series analysis is going to help us determine how do we set the proportionality constant when we are inspired to come up with a scheme for approximating derivatives.